the recorder. And what we'll do today, I'm just going to restore the whole session. What we'll do today is to go over the practice exam, and it also serves as a review of the material that you need to know for the exam, which is 1 week from today. Is that so? You need to let me know if you do not make it on that day. No, this is not your homework. This is from another class. I'm just restoring a session. So let's go to this class here. And the link to the practice exam is in discrete probability distribution. No, I lied. It's the next one is in recursion. Just skip over. Where is it? Yep. So it's practice exam 2. That's the link to the practice exam question. There was one thing that I wanted to share. Oh yes, I sent you guys an email or a notification through the news forum about a internship program for the BCS division. If you open it up, you will see the instruction. If anyone is interested in getting internship, you can contact that particular person. Does anyone know what I'm talking about? Okay, you checked the email? Okay. So I'll just kind of quickly go over that one first, and then we'll continue with the usual class material. So this is the email that I sent to the entire class this morning because I just got a flyer this morning. And this is the document that basically just kind of describes what the program is about. So if you're in the BCS division, which you are in because it is computer science, you can contact this person, either Dr. Samia or my child Thao, or contact by this email address and express your interest in getting into an internship program. The program is getting put together right now, so they're gathering interest from students, and at the same time these people are trying to get employers interested as well. So we are trying to make connections on both sides, and depending on your interest and depending on the demand from the employers, these people will try to make a match so that if you're interested in, let's say, IT work, and the other side also has IT student internship, they will make the connection. Okay, so for anyone who's interested, go ahead and contact these people, and you probably want to just not just mention your name, but also your interest, what classes you have taken already, and that sort of information, so they can make the connection a little bit better. Are there any questions about this particular internship program? This is not a campus-wide internship program, so this has nothing to do with the Career Center at all. This is specific to the BCS division. Yep?
When you say that for credit, does that mean that they only last for 4 to 6 months, as long as a semester?
That is correct. So the way it works is once you sign up for an internship program, you actually have to take a work experience class, a WEXP class, and for the duration of your internship, you will receive credit for the internship. But you won't be taking any classes here, so you'll be working at the employer, but you'll be collecting credit that will also show up on your transcript when you're done with your program here.
Okay, so then 2 more questions. The first is, obviously you don't make any money on this because it's for...
You might. You might. Yep.
And then the second question skipped my mind, but if I remember, I'll come back to it.
Okay, well, it is useful because a lot of times, when you are ready for your actual real job, they will look at your resume, right? Now, if your resume only lists, I have taken classes, or I'm a really good student, well, that's all good. But if the next person has the same GPA, has the same, academic performance, but that person also has, internship, on the resume, that person will get preference. because knowing what it is like at work definitely helps to get your first real job.
My last question is, do you know about how many hours a week they require you to work?
We do not know yet. I think it varies, and that's why you can earn 1 to 4 work experience academic credit, depending on the number of hours you have to work. Right now, I think some of the real potential employers are the state government, agencies of the state government or boards of the state government, like the Board of Equalization, the Franchise Tax Board, and a few other departments or boards that are well known to have a really good sized IT department. Reclamation, okay, so that's another one. But even smaller, sections or branches, sometimes they have their own, IT, requirement as well. So, it's not a bad idea to at least, look into, internship. Because I know most people in this class are planning to transfer to a 4-year university, but if you have the time, I think they're trying to put this together by the summer. In other words, you'll be able to sign up for an internship, assignment during the summer. And if you're not taking any classes in the summer, you might as well use it to get some work experience, and so you can put it on your resume when you're ready to get your first real job. Right. So are there any questions? No questions. Nobody's worried about getting a real job, right? I mean, you guys are all focused on, getting to a 4-year university. A real job, oh, that is so far in the future. I don't want to think about it. Some of us do. Some of us already have, the first job. But the first job is very important because, that's how, you can write on your resume to get your second job and so on. So here's a quick question. What is the average amount of time people spend in the same company, at the same job, in the high-tech industry?
2 years and 11 years.
Sorry?
Probably just a year.
Well, a little more than that. It's between 2 to 3 years. Okay, so people stay at the same job, for about 2 to 3 years, and then they move on.
They get offered a better pay.
Well, it works to a certain extent, but not, all the time. The companies, the high-tech companies in the Bay Area are starting to realize this is what people are doing, so they change the job every 2 to 3 years, and every time they change the job, they go for a higher pay. So now, all the top-tier employers are talking to each other, and they establish like a standard. So no matter where you go, they will put a cap on, your salary. This is also the reason why they're pushing programming to middle school and high school programs, to crank out more, programmers, so they don't have to pay as much money to hire, developers. But not the good ones. Not the good ones. All right, so let's take a quick look at the test first, and I'm going to kind of magnify a little bit so you can see better. The first question I think is really quite interesting. I think some of you might have thought about this or have heard about this type of question before. If you consider a class of I'm just using 30 students here because that tends to be a nominal size for a regular class. Not for this one, obviously. This class has about 50 students. Express the chances of at least 2 students having the same birthday, and I'm not talking about birth date. Okay, so the year is not a part of the consideration. Just considering the month and the day of the month, and we're not going to take leap years into consideration. So February 29th is not going to be considered. You can use the combination, permutation. That's what the C and the P are for, and also factorial if you want to use factorial in the final answer. You don't have to actually give me the exact number. You can just say, okay, this is how to compute the exact number. All right, so this is the question. I have 2 questions, okay? There are 2 things related to this one. The first one is, according to your estimate, okay, what kind of number are we talking about here? What are the chances that in a class of 30 students, that at least two people will share the same birthday? Okay. Do you think it's going to be somewhere around 0.01, or 1% as a chance, about 10% as a chance, 50% as a chance, 75% as a chance, or close to 99% as a chance?
Probably somewhere around 1%.
Let's say you've got about 1/3%.
1/3%. So 0.003333. Okay, go ahead.
I think I heard of this problem a long time ago, maybe like on the internet. I think it's around 50% or something.
It depends on the class size, okay? But 50% is probably for a class of about 25-ish students. For 30 students, it's actually 70%. Yeah, there's a pretty high chance that in a class of 30, that at least 2 students would have the same birthday. Now, this class has about 50 students, so the chance would actually go up to, I would guesstimate, to be at least 85%. So there's an 85% chance that in this particular class, 2 people will share the same birthday. Okay? So let's go ahead and figure out why there's such a high chance to do this. Okay? So what I'll do is I'm going to do this. If you scroll all the way to the end of this document, the answer is there already, but I'm going to work on it step by step here as well. Okay. So the way we want to do this is to calculate the probability of exactly the opposite. In other words, what are the chances that no one in a class of 30 have a duplicate or share the same birthday? I want to calculate that first. And then we can take 1 minus that number as the actual answer to this question. Are we doing okay so far? Does everybody understand why they're opposite to each other? The chances of having at least 2 students sharing the same birthday is exactly the opposite of the chances of not having anyone sharing the same birthday. Is that okay? All right. So what we'll do is we'll calculate that particular probability over here. So this is the chances of no one in a class of 30 sharing a birthday. Okay? In other words, all 30 students have unique birthdays in this particular case, and what are the chances of that happening? So I'll do this in an equation. Yep, go ahead.
Is that because of the at least? Like if it was exactly 2 students, would you have to do something else?
Say again?
Is that because of the at least? If it was exactly
It's
2,
because of the at least, yes.
Okay.
Yep.
If it was exactly 2, would you just do a different
If it's
method?
exactly 2, then the chances will be lower,
Yeah,
but it will still
smaller.
be pretty high though. All right, so I'm going to use the equation ability of Google Documents, which works fairly well. It's okay. All right, let's take a look at the first student. Now, for the first student, how many choices do we have? The first student can choose any day out of the 365 days, right? There's no chance of colliding with another person because this is the first person that we're considering. Okay, so the first person can choose 365 days out of 365 days and not have a problem. Is that okay? Does that make sense? All right. What about the second student? The second student, I'm trying to get into the right place. I think, no? There we go. So the second student can choose 364 out of 365 days. Does that make sense to you?
Yes.
Okay. All right. So we have 364. Oops. We need to specify a fraction again. 364 out of 365 days. So together, if I only have a class of 2 students, the chances of those students not sharing the same birthday is going to be pretty high. It's going to be 1 times 364 divided by 365. Does that make any sense to you? If I only have 2 students in the class, okay, the chances of those students not sharing the same birthday is, basically, pretty close to 1. That makes sense, right? Okay, let's consider the third student in this particular class. The third student is going to be able to choose from 336 363 days out of 365 possible days, and not have any collision with the first two students. Is that making any sense? Now the rest, I can write it out, but it would just be wasting time, right? So I can just use dot dot dot. And then we can conclude the last one is going to be, the last one is going to be 365 minus 29, and then divided by 365. The reason why we are subtracting 29 and not subtracting 30 is because we are subtracting 0 from the first number, and then we have 30 students. So the last one is only subtracting 29 instead of subtracting 30. Are we still doing okay so far with this calculation? Haven't we seen something like this? There's another way to express the numerator of all of these fractions. Yep.
If you let the number of people in the class equal, let's say, letter n, then you would just do 365 minus n minus 1.
Correct. Yeah, in general, if
In general, yeah.
if n is the number of students in the class, then you can just say 365 minus n minus 1.
Yeah.
No, plus 1, because unless you put the minus 1 in parentheses.
Yeah, the n minus
Yeah.
1 is all in
Yeah.
parentheses, minus the quantity n minus 1.
Right, but we can also simplify this in a certain way, because what is, okay, I'll just test your knowledge of this thing here. What is the other way to express 7 times 6 times 5?
7 factorial
Is,
minus
okay, that's very good.
4
Okay, so
factorial.
it is 7 factorial divided by 4 factorial, but there's another name for this too. Come on, what is that calculating? Permutations, all right. This is calculating the number of permutations of choosing 4 out of 7 items, otherwise known as P with a 7 on top, a 4 at the bottom, or 7P4, or P and then 7, 4 in parentheses. So these are all basically doing the same thing. It is the number of permutations of choosing 4 out of 7 items. What can I do about that one? Can I apply something like this to simplify that equation? Well, at least with the numerator. Yep, go ahead.
You could do 365 factorial over 336 factorial, and that would take care of that. And it's
You are close. We can do the number of permutations of choosing out of 365 items, 30. Because the number of permutations of choosing 365 out of 30 items is 365 times 364 times 363, all the way down to 365 minus 29. Okay. What about that's the numerator. How about the denominator? What can we do to make it a little bit easier to read?
365 to the power.
Yep, 365 to the power of 30 in this case. All right. And what do you think this number would add up to? I mean, I kind of mentioned that a little bit earlier in class. So to do this, we can, let's see, I'm just trying to, well, let's go ahead and give it a try. So what we'll do is we'll try out cisp440, go to exam 2, and I'm going to create a new Google document or Google Sheet. So this way we can see if we can do all the calculations here. So we are looking at the number of permutations. We have 365 days to choose from, of which we only want to choose 30 because there's a class of 30. That is my numerator. My denominator is based on the power function. We are calculating 365 to the power of 30. And that number turns out to be 0.2936 blah 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 blah. Okay? But this is not the answer that I'm looking for. This is the opposite of the answer that I'm looking for, because this is the chances of not having anyone in class sharing the same birthday as another person. And that was a hand a little bit earlier. Let me address that first. Was there a question? No? Okay. If there are no questions, we can now say, okay, but what is 1 minus this particular number? Because that really is what we're looking for. And the answer is 0.7063 something. So approximately 71%. There's a 71% chance that out of a class of 30, that at least 2 students would have the same birthday. That's pretty high if you think about it. Okay, that's a pretty high probability. Yep.
On the test, how much of this work do you expect us to show before we get the answer?
Mostly just explanation. You know, why do you multiply 365 and then 364 and then 363? You know, why is that number decreasing, and why is the denominator not decreasing? Because you have that many days to choose from, but the correct choices would be 363, 362, and so on. So I'm looking for the explanation, the reasoning, and not so much the calculation. You don't have to come up with this calculation, because for people who do not have a calculator, it will be pretty hard to do this kind of calculation. So as far as calculation is concerned, you can just express the equation itself and say, this is the number, but I don't know exactly what value is that number. All right, so if that is the case, let's think about it for this class. Okay, I think there are still about 50 students in this class, so we'll go ahead and calculate that probability. So let's go ahead and copy and paste it a few times over here. And this time we are dealing with, let's say, 50 students. So we'll put 50 and 50 here. So for a class of 50 students, there's a chance of 97% that 2 people in this class share the same birthday. In other words, it's almost a certainty that someone in this class would have the same birthday as somebody else.
We should test it. We should test that.
We should test it, right? Well, if I just throw a number, that's going to be pretty hard. But if you think about it, it does not seem to make sense, but yet it does. It doesn't seem to make sense because there are 365 days in the year. And even with 50 students, we are only hitting, what, about 1/6 or 1/7 of all the possible days. But even so, the chances of 2 people having the same birthday is almost 1. Okay, it's 97%. That 2 students, at least 2 students, will share the same birthday. And this is not even taking into consideration, twins and stuff like that. I mean, are you guys kind of surprised or not? You guys go like, yeah, the numbers just kind of works out. But intuitively, I find it kind of surprising. Okay, well, let's go for the other extreme. Okay, let's go for the other extreme and make sure that this method of calculation is actually correct. In other words, what if I have a class of 1 student? Okay, if I have a class of 1 student, what are the chances of that 1 single student share the birthday with someone else in the class? It ought to be 0, right? So let's plug in that equation and see if it works out. Now this is the sort of thing that you kind of should be asking, when you're working on a problem. So I'm looking at the permutation of 365, choose 1, because I only got 1 student, and the denominator is 1 as well. And you can see there's a 100% chance that no one in the class shares the same birthday. Well, guess what? There's only 1 person. There's no such thing as sharing the same birthday. Yep.
Is this irregular computational logic, or is it just because the computer can't display something divided by 0?
No. This is correct because, okay, what is P? What is the number of permutations of choosing 1 item out of 365?
365?
No.
Oh wait.
You're choosing only 1 item out of 365, but the number of permutations is asking how many different ways can I arrange it.
Oh, just 1.
No, well, this one is 365. Okay, you are correct. This is 365. There are 365 ways of rearranging one thing out of 365. But the denominator is also 365 to the power of 1, which is also 365. So that is just 1. So that's why it works out to be 1, but you have to remember what the 1 means. It is the probability that no one shares the same birthday in the class. So you have to do a 1 minus that number to get the chances of at least 2 people sharing the same birthday, and that works out. Is that okay so far? Okay. So that's the first question. And since we're already in the mindset of working with probability and stuff like that, I'm going to skip, oh, this is the wrong test. They have the same name, that's why. So I will skip to question number 6. And it's all the way over here. And it's your favorite topic, Lotto, right? So this one is the real one, okay? This is actually the California Super Lotto Plus. In this game, there are 5 lucky numbers, and each one you can pick from 1 to 47, but you cannot use 2 numbers, okay? In other words, you will pick unique numbers from 1 to 47, plus 1 mega number from 1 to 27. That one is independent to the first 5 lucky numbers. In other words, they put everything back into the basket in order to determine what is the mega number. And the mega number can only go from 1 to 27. Is that okay? Does everybody understand the rules of the Super Lotto Plus? Okay, yep.
I ask you a question about the first one. I'm sorry to go back, but
Okay, go back.
when you were doing, like, showing the series of things you were going to do, the last number you did was 365 minus 29. So, like, why are the permutations? Because essentially, like, when it does the equation, it's going to do 365 minus 30 factorial.
That is because of the definition of permutations. Okay, so if I go back to, let me just, I'm going to use mousepad to describe that. Okay. So if you have n times n minus 1 times n minus 2 times n minus k plus 1, okay, that is the number of permutations of choosing k items out of n. But that's exactly what we have. Because we have 365 times 364 times blah, 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 all the way down to 365 minus 30 plus 1. That's why we have the minus 29 at the end. Is that okay?
Yeah.
All right. All right, so getting back to the Lotto thing, okay, for the current round, okay, the current drawing, there were 14,540 winning tickets that got 3 out of 5 lucky numbers, but not getting the mega number. I just pulled this out of the Lotto website, so this is actual number. Okay? So the first thing I want you to do is to figure out the odds or the chances of winning 3 out of 5 lucky numbers, but not the mega. Okay, and the prize money is $10 for that particular prize. And using this number, I want you to guesstimate the actual number of tickets sold because it should be proportional. Is that okay? Are we doing okay so far with this question? Okay. So there are actually several things you have to work out first. Okay. The first thing you have to work out is how many different tickets is possible. So once again we're looking at the number of unique tickets possible. But in the case of California Lotto, the same ticket can be issued multiple times. Or multiple people can purchase tickets that have exactly the same 5 lucky numbers and the same super number. Is that okay? Yep, the mega number.
So then the idea is to figure out if in a game where not all the numbers are sold, or all the numbers are sold one time, I should say, how many winners you should have, figure out how many multiplication, or how many
duplicates.
Possibly
Duplicates. So we don't know, we don't know yet, okay, So we are using this as an estimation, all right? All right. So out of the 5 lucky numbers, okay, we first have to calculate the number of winning tickets that can get 3 out of the 5 lucky numbers, but not the mega number, okay? So what is the number of combinations, in this case, of tickets of that kind, unique tickets of that kind?
Do you want to do combination of 3 out of 5
Of the
times
lucky numbers?
Combination of not getting, or of getting 2 not lucky numbers, which would be.
So 47 is the total.
2 out of 42.
2 out of 42 is correct.
Times not winning the mega, which is 1 to 27, so you times 26.
Yep. So this would be the number of unique tickets that would correspond to winning 3 out of 5 lucky numbers and get $10, as a prize. Does that make any sense? Okay. This is kind of the same thing as what we did last time, except instead of the color permutation, we have a mega number. Question?
Yeah, so you can set that equal to like 14,540. Are you going to set that equal to the number of winning tickets?
Not yet. This is if all the tickets are unique. Okay. In other words, if we do not issue duplicate tickets, this will be the number of tickets that will basically have a $10 prize. So we want to calculate this number first, and we'll go to our spreadsheet for this calculation. So combine 5 out of 3. These are the lucky numbers. And 42 out of 42, we choose 2. These are the not so lucky numbers. And then times the 26, which is the wrong mega number. Okay. So this will give us an error.
Put another comment.
Yeah.
Yeah.
Oh yeah. There we go. This will give us, pretty huge number. Okay. So potentially, if all the tickets, all the unique tickets are sold exactly once, there will be 223,860 tickets winning $10. And how many tickets were actually sold? Or how many tickets actually got the winning number? That is in the question itself. And it is
14,500.
Open on tab 3.
tab 3. Check. So we only got 14,540. Okay, so let's go back to the spreadsheet. So 14520.
540.
Okay. 40. Okay. There we go. So this is theoretically, there are that many unique tickets that can be winning $10. Only this many are actually sold, so only this many people can collect $10. Okay. This alone cannot tell us the total number of tickets yet. Okay. So we want to calculate what is the total number of unique tickets for Super Lotto. Well, that number is going to be what?
Combination of picking 5 out of 47.
Yep. That's for the lucky numbers, and then times 27 for the mega number. This is the exact number of unique tickets that can be sold. But as I said, in California, they can issue the same ticket over and over again, or the same combination over and over again. All right, so this is the ratio of this number divided by this number should be the same as the ratio of this number divided by this number, which is what I want to know. Okay, I want to guesstimate how many tickets were actually sold for this round of Lotto. So are you guys understanding the problem? It's just a ratio in this case. Okay, once we figure out the numbers, it's just a matter of ratio. So this number should be this number times this number divided by this number. Okay, let's double check and make sure that it does make sense. Does it make sense to you? What is A5? A5 is the total number of unique tickets that can be generated. B4 is the actual number of 3 out of 5 winners. And then A4 is the potential unique tickets that can also be the 3 out of 5 winners. So the ratio should be preserved here. Let me just press the enter key and you can see for yourself whether the ratio is preserved or not. So when you look at 225,000 or 224,000, if you will, out of 41 million, it should be the same ratio as 14,000 over 2 million something. I think the ratio works out. Does not work out? Well, we can always double check, right? This is a spreadsheet, makes it very easy to check out stuff like that. This number divided by this number is just a ratio that I'm looking for here, and you can see the ratio is the same. So this means for this particular question, my guesstimate is about 2.7 million tickets were actually sold. Is that making any sense? Yep.
What does the number in A4 represent again?
Say again?
What is the number in A4?
A4 is representing A4 is representing the number of unique tickets that should win the 3 out of 5 but not mega prize. Which is, this is the theoretical number of unique tickets. The other number on B4 is the actual number of tickets winning that particular prize. Yep.
I'm not really understanding how this takes into account duplicates.
Say again?
I'm not really understanding how this takes into account duplicate tickets.
In this case, probably very few, if any, duplicate tickets were sold.
Okay.
Because we actually have, okay, let me press the enter key. So we have 224,000 unique combinations that can be the 3 out of 5 winning tickets, but we only sold 14,000 something. So the chances of a duplicate ticket was actually sold is pretty low.
Oh, so we just ignore it.
Yep.
We actually sold about 6.5% of the total number of combinations.
Right. So now the question is the state making money or not?
Yep. So wait, so is the 2.7 million, is that unique combinations?
Not necessarily. That's just an estimate of how many tickets were sold. There's no way to tell how many of those are actually unique and how many of those are just guesstimating. This is the number of tickets sold, just as a proportion. Because the proportion between A4 and B4 should be the same proportion between A5 and B5. That's basically how I did the calculation.
Yeah, that's why what I was thinking. I think that this is the second column is still unique combinations because the ratios match. Because the first column is with the assumption of unique tickets.
Right.
So the second column is just the reason why it's the same ratios because it's furthering that assumption with just a smaller number of tickets instead of the maximum number of tickets.
Right.
Because if there were duplicates,
There might
the
be
ratio
duplicates
could be
within that
different.
number, but we don't know whether there is or not. But the number of unique, well, I guess the chances of having a unique duplicate number of 3 out of 5 winning is the same as the chances of having a duplicate of general ticket population. So it will still be the same ratio. Is that okay?
I think so.
The ratio between this number and this number should be preserved in the number of tickets actually sold.
What I'm thinking of is that the ratio would be preserved if you're still just talking unique tickets instead of allowing for duplicates.
But the chances of having duplicates would be the same whether they're winning or not.
Right.
So the ratio would still be preserved. So even if out of these numbers, a certain percentage are duplicates, it will still be the same number of duplicates, in here, assuming that is the same distribution function. Is that all right? Okay. So the state actually did not sell a whole lot of tickets. 6 point something percent of all possible combinations. All right, so if that is okay, then we have handled all of the questions related to probability. So we'll go back to the other questions now. Question number 2 is resolution by refutation and proof by contradiction. I'm not sure how many of you still remember that stuff, so we'll go ahead and we'll try to remember what is resolution by refutation and what do we need to do to get started. Yep, go ahead.
My question is, are you going to be providing a list of axioms again?
This one does not need a whole lot of axioms.
No, but
This one only has one rule. Basically, if you have to first turn everything into CNF, the conjunctive normal form, right? And the test is open book, open notes. You can bring anything that is either written or handwritten prior to the test. So if you find anything on our website to be useful, if you find anything on Wiki that is useful, if you find any book in the library that is useful, bring it along. Okay, so that's why I'm not going to give you, the list of axioms, because you can print it out if you need to print it out. Okay. All right. But to answer this question, the first thing we need to do is to convert everything into CNF, the conjunctive normal form. Okay. All right. What is given to me? I have to first convert that into CNF. We have P is equivalent to Q, and P, those are the given facts. So we have to convert everything that is given to me into CNF first. Well, let's deal with the first one first, which is P is equivalent to Q. Well, how do we convert this one? Remember, in CNF, you can only have disjunctions and then conjunctions. Go ahead.
P implies Q and Q implies P.
Okay. Okay, that's a good start. Let's go for that one. So P implies Q, and Q implies P. Okay, that's good. That's by definition, that is the first step. And then what? We have to go from implication to disjunction. How do we go from implication to disjunction? Conjunction, sorry.
Not Q or P.
Yep. So the first one is not P or Q, and the second one is not Q or P. Is that okay? Okay, now if we look at this portion here, is that in CNF?
Yes.
It is in CNF because we have disjunctions as sub-expressions, and within each disjunction sub-expression, it's only involving either just variables or the negation of variables. And then the outside, we only have conjunctions. So this is good. The second thing that we also know is P all by itself. Okay. So that means the CNF of all known facts is just going to be, yep, exactly. It's just going to be this particular CNF and P, which together is one big huge CNF. Well, not huge, but bigger CNF.
Which is going to take like one step to prove.
Yes. Well, no, 2 steps. It will take 2 steps to prove it. Because what we're trying to prove is Q is a result. In other words, if you are given that P is equivalent to Q, and you're also given that P itself is true, I want you to tell me, that Q is also true. So Q is a theorem all by itself. Q being true is a theorem all by itself. So does anyone still remember how to prove by contradiction in this context of resolution by refutation? Yep.
Find a way to find 0 in the equation.
And
Not yet. Okay, you're getting to the good part, the juicy part. But before we get to the juicy part, there's one more thing we have to do.
Insert the negation of what you're trying to prove into
Yep.
what you know.
Add the negated theorem to the CNF. So what we end up with here is not Q, not P or Q, and not Q or P, and P. That's the known fact. Now we have to introduce not Q as the negated theorem. The very same thing that I want to prove but the negated version of that. Because if Q is actually a consequence of the known facts, and I put the negated version of it here, I should get to a contradiction. That is the whole idea of proof by contradiction. Okay. All right. So let's see if we can get to a contradiction here. How do we do refutation again? What do we need to find?
0.
That's contradiction. Okay, but I'm just worrying about the refutation process. Yep.
So you have to find 2 terms that contradict each other.
Yep. So you will have to find 2 terms where each one has the non-negated version of a variable, and the other one has the negated version of the same variable. Then you can combine those two, get rid of the variable where one has the negated version and one does not have the negated version, and combine the rest, right? Okay. So we can start with many things. Okay, we can start with P, we can start with not Q. It depends on how you guys want to do it. Let's start with P and not P, okay? Then go ahead.
P and not P?
Yep. So we can combine. Now we can work with these two, okay? But that's not going to get us anywhere, okay? So we'll go ahead and combine this term here. I'm just going to highlight it, so this way we have. Come on. Yep. Paint format. Okay. I'm trying to look for the.
It's in the format or.
Under format. I know I can change the color of something. I just cannot remember how to get to it.
Or if we just bold it.
Just hold it. No, it's too long. I cannot see it. I think that's
fine.
fine.
Just at the top, just bold it.
Sorry?
Control B.
Control B. Oh, okay. Just boldface.
Yeah.
I was looking for the color option so I can change the color, but I guess boldface works just as well. That's fine. Okay. Okay. So if I combine these 2 terms, using the refutation process, what do I end up with?
Not P.
I have to repeat the first portion because everything that is already here should still be here, but I'm adding one more term.
So you get not P
And Q.
and P for Q and P.
Right. So this P is basically the same thing as P or false, right? Okay. And this one is Q. This one has a or Q. So we will combine the Q and the false, the implied false.
Yeah.
So it becomes Q or false. But anything or false is just whatever the original thing is. So we end up with Q as a new term. Is that okay? So that's the first result. The second one, obviously, is just going to be combining these 2, right? Yay.
The really cool thing is if you're
Whoops.
the link with Google Doc, you can see you editing.
Yeah,
in real time.
yep. You can see all the mistakes that I'm making along the way, and yep,
Hey, look at that.
yep. So we're all done. So this one turns out to be pretty easy to prove. Yep. Go ahead.
Could you just, on the second line, just combine the third term and first terms, the not P or Q and the P, and then a Q comes out? That's what you're looking for.
Okay, let me try to get to that one. The second line?
Yeah.
On the
Oh,
second?
I'm sorry, even higher. Just
This one?
The known facts.
Uh-huh, the known
CNF of
facts.
all known facts. You start with the not P or Q, and then the third one is P. So if you combine those, you get Q, and that's what you're looking to prove.
You can do that too, right? Yep.
This is one step.
Let's see. So you're combining this term.
Just basically without assuming the negation, you can just from expansion.
You get not P or P and P or Q out of that when you combine them. When you combine not P or Q and P, you get not P or P and P or Q. When you do that combination.
When I do which combination again?
Not P or and P
What?
or.
No. Not P cannot be combined with anything else because we only have one term that has not P in it, and that's not P or Q. need to give you guys laser pointers so this we can
Oh, because with resolution with resolution refutation, you can't. You have to have the other thing has to exist inside.
Right. You can only take two terms out of the CNF and say these two can combine into a new term. So out of the first line, which two are you?
I was thinking the first and third, since you have not P.
The first and third. Okay, so let's go for the first and the third.
Doesn't that just
So
produce Q?
Yeah, if you combine these two, you get Q left, right? But you still need one more resolution to combine the Q and the not Q. So you still end up with the same number of steps.
Oh, right, because what I was saying is instead of doing a proof by contradiction, since you're trying to prove that Q is in there, don't you do that
okay,
just by
I get you.
producing Q?
Yeah, but the question is asking you to use only resolution by refutation to prove it.
Okay. Okay.
Yeah.
I got you.
Okay, so I understand
If you
your
just do a simple expansion, you get what you're
right.
doing.
You can use the simple expansion and use the other axioms, but that's not what the question is
Okay,
asking. The
I
question is
understand.
specifically asking
Use
so that you can show your skills in resolution by refutation.
Okay.
Yep. Okay, now I understand your question, your suggestion of, oh, this is easy. We can just do it with one step.
Yeah.
You can even do it with a truth table if this is not being asked. A truth table will show that any rows with P being true, Q is also true as well. You're done. Yep. Okay, question number 3. Question number 3 is about coin tossing. Assuming that you have an even coin that is not loaded, what are the chances that exactly 4 out of 100 tosses are heads and the rest being tails? Do not give me a single number. There's no need to give me a single number. Express your number using just terms. Just give me the equation or the formula to calculate the probability. Now, given the fact that you can print out all my notes, this should be an easy one because it is on one of my notes. Okay. Okay. First thing first. How many ways can I arrange 4 heads out of 100 coin tosses?
P 100, 4.
Not P. We're close.
Sorry, C.
Combination is a C. Yep. Okay. So we have the number of combinations of arranging 4 heads out of 100 coin tosses is this number. Now, for each sequence of 4 tosses, 100 tosses, excuse me, for each sequence of 100 tosses, what is the combined probability of getting 4 heads? And remember, we have an even coin here. So that would be 0.5 to the power of 4, right? What are the chances of getting 96 tails? Same thing, right? 0.5 to the power of 94 in this case. 96, sorry. Yeah, I look at one thing, I say another thing. Yep. And that's the answer. Okay, this is all I'm looking for. You don't have to actually come up with the number, but this is a pretty small number. In other words, the chances of only getting 4 heads up out of 100 coin tosses with an even coin is pretty small. If that is what you're observing, you can say, well, what are the chances that coin is not loaded? Pretty slim. Okay, that's number 3. Number 4. Number 4 is interesting in a way. It is asking you to prove something. Okay, but this one is relatively easy to prove. It is not going to be a difficult one. I'm not asking you to prove the binomial theorem or the Pascal's identity. Yep.
Sorry, I wanted to go back to the last one for just a second, but
Yep, go ahead.
in the first example we had permutation 365 out of 30 over 365 to the power of 30. And this one we don't divide by 96 or anything, divide by anything.
Because a half is 1 divided by 2.
Oh, so we are doing 1 over 2.
You're doing the combinations over 2 to the power of 4 times 2 to the power of -2.
Okay.
Because each event is independent from the previous one. So every time you toss the coin, that probability of having a head instead of a tail is independent of what happened in the past. Assuming the coin tosses do not in any reasonable way bend the shape of the coin so it becomes loaded. It's always possible, right? All right. Question number 4. Question number 4, I think, is one of the more interesting question. It is not a number type of question. It is a proof type of question. So I want you to prove by induction. Use proof by induction as a technique. And the second proof is the wrong proof because it is a verb and not a noun. Prove that n factorial is the product of I going from 0 to n. You are given the definition that 0 factorial is defined to be 1. And then for all of the other integers from 1 all the way up, x factorial is x times x minus 1 factorial. So I want you to do this proof for me and use proof by contradiction. Now, whenever we're dealing with proof by contradiction, yep, go ahead.
In the pi, I think I should start from 1. In the pi, I from 0 to n, I think I should start from 1. So.
Oh, it should be 1, yep. Otherwise, the whole thing's going to be 0. Yep. Good catch. All right. So can we prove this? Well, what is the first step in any type of proof by induction?
Base case.
We need a base case, right? Okay, go ahead.
It makes sense to make that second part of the question your even definition that 0 factorial is equal to 1. That's right.
Well, it will still be okay. I mean, you can still prove the base case as 1 factorial first. The base case does not have to be the definition that is given to you. It just has to be given this number, the theorem is true already. That's basically what you need to do, is to say in one single specific case, okay, the theorem is true for that one specific case. Okay, so I'm going to show you exactly what I would do with this. Because in this case, the base case does not meet the general form of n factorial. So we are not quite ready to do that yet. Okay, so let's take a look at the base case. So I'm going to say the base case is going to be 1 factorial. This is what I want to use as my base case. But hold on a second here. 1 factorial is not the definition. That's okay. Use the recursive definition. Because 1 is a part of the recursive definition. So that means by the recursive definition, 1 factorial is going to be 1 times 0 factorial. Is that okay?
Wouldn't it be?
But 0 factorial is by definition 1. So what would that make 1 factorial?
1.
That would make 1 factorial 1. Okay, so that's good so far. But is that also going to be the same thing as the product or the pi of I going from 1 to n1? Okay, does that make sense? Okay, in other words, can I insert equation? And I cannot remember how I did the pi, but that's okay because I can do this. Yes, I did. I'm cheating a little bit here. So it goes from 1 to 1, and this is I equals 1 to 1, and this is I here. Are you guys convinced that I can rewrite that 1 as the product of 1 all by itself? Okay. Is that meeting the theorem? It's okay, right? So the theorem says, yes, so now we have a base case. The base case is now proven. What is the second thing you have to do with proof by induction? Now that we have a base case, what is the next step? What is the name of that step? The sentence that I just said, already has those words, but not in the right order. It's called the induction step. Okay. So what do we have to do about the induction step? We extend from n minus 1 or k minus 1, whatever, to k, right? But we are also going to make a very important assumption. What assumption are we going to make when we prove the induction step? The one thing we can make an assumption of is the theorem is true for case 8k minus 1. Okay, I'll just go ahead and write it out, and then we can just look at it and kind of talk about it. Okay. The induction step is basically saying assume the theorem is true for k minus 1. So this is a very important assumption. We are basically saying we don't really know whether the theorem is true for all cases, but we will make the assumption that it does work for k minus 1. Now, assuming that the theorem does work for k minus 1, or case k minus 1, prove that it also works, the theorem also works for case k. That is the induction step of any proof by induction. Are we doing okay so far? Any questions about this step? What was the theorem again? Let's go check out the theorem itself. This is the theorem. Okay, so I'm just going to copy and paste this over here. All right. So if the theorem is assumed to be true for case k minus 1, I'm just going to be lazy and go here and say k minus 1 factorial is, according to the theorem, assumed to be true, is going to be this expression. Are we doing okay so far? I'm just applying the general principle of proof by induction to this particular case. Okay. So I'll just make it even more clear and say, so we are basically assuming this is already true. Now, if this is true, what about k factorial? According to the recursive definition of factorial, k factorial is k times k minus 1 factorial. Are there any questions about this particular statement? It is by definition, it's by the recursive definition of factorial that we can establish k factorial is k times k minus 1 factorial. Okay. But once you establish that, what else can you establish? Well, let's take a look. I'm just going to copy and paste again here because I'm going to calculate k factorial as k times k minus 1 factorial. But we already know k minus 1 factorial, which is this part here, is the same as this entire pi sign. So I can just now take this pi sign and say, hey, I can just multiply k to that whole thing, and this is now k plus 1 factorial. Are we still doing okay so far? Because of the assumption that the theorem works up to k minus 1, I can make the substitution. K minus 1 factorial is the pi sign from I equals to 1 to k minus 1. Is that part okay? Yep.
Why did you change the variable from n to k? Is that necessary? Or can you just keep it as n?
You can keep it as n, I suppose.
Okay.
But when you're doing the induction step, we typically pick a different symbol from the quantifier symbol that we used earlier. But is this step okay? Going from k plus 1, the whole thing factorial, to the pi symbol, going from 1 to k minus 1 I. Okay. But when you look at this expression, let me just kind of highlight the expression that we're dealing with here. when you look at this expression, is there a way to simplify it? Can I absorb the k into the pi, into the product term? Okay, let's write it out a little bit. Okay, just kind of write it out a little bit. Okay, so we have k all by itself on one side, and then we have the pi notation, which is a product of a series of numbers, right? So the pi itself expands to what? K minus, well, okay. Because we're going from 1 to k minus 1, so we'll go ahead and use that order. So it's 1 times 2 times blah, 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 and then the last one is k minus 1. This term here is the pi term, right? Because this is basically pi of I going from 1 to k minus 1. Is that okay? I have a k on the outside. What if I move this k to this side and remove things a little bit? Then I can say, hey, now we have something that looks like this. We can take away this in parentheses, put it here, and now I can change the pi term to just I going from 1 to k. Is that making any sense? Right? So I'm just going to write it down here. So this whole thing equals to the product of I going from 1. Thank you. for your enthusiasm. I know you're tired. Yeah. Okay, would that work? I'm just absorbing k into the pi term. Can someone remind me what is that term? What is the last term? How is it related to the whole thing that we're trying to do? Now we have just proven that it is also, the theorem is also true for k. Okay? From the assumption that it works for k minus 1, and because of the definition, the recursive definition of factorial, now we can prove that it also works for case k. Well, we have the induction step proven. So with the base case and the induction step proven, what can we do now? We're done, okay? So with both a base case proven, okay, base case and induction step proven, the theorem is proven. That's proof by induction. Do we have any questions about proof by induction? We saw this the first time when we were dealing with, I think it was the binomial theorem. And this is the second time that we are dealing with this. Yep.
I never really understood what's the point of the base case.
The base case gives you a ground to step on. The induction step is basically, it's assuming that if you have one step of a staircase established, you can step onto the next one. But the whole staircase still has to be grounded at some point. The base case is where it is grounded. If you only have the induction step, it's not going to be helpful because it only shows that if it does work for k minus 1, it will work for k. You can work your way back, but where do you stop? Do you know what I mean?
Kind of.
Okay, it's kind of like this. For each case, you say, well, by the induction step, I know that I'm okay because the guy who's before me is okay. So now you ask the guy before me and say, how do you know that you're okay? And he says, well, I know I'm okay because the guy before me is okay. So you find the guy before him and ask him, why do you think you're okay? And so on, right? But you have to stop at someone because you cannot keep asking this question forever. So eventually it will get to one single guy, which is the base case, guy or gal, which is the base case, and you ask, how do you know that you're okay? that person can no longer say, I know I'm okay because the person before me is okay. That person will be your base case and say, I know I'm okay because here is the proof of I'm okay, not relying on the theorem itself. Okay. The problem with only using the induction step is it is already assuming the theorem is true for case k minus 1. And that is a big assumption. And that assumption has to end at some point in order for this whole thing to be grounded. And that will be the base case. And when you look at it, the way we prove the base case, it does not rely on the theorem being true to begin with. It is actually a direct proof going only in a positive forward direction to prove that the theorem is true for the case when k is 1. Yep.
Does that mean that for the base case you have to use like numbers and not variables?
Right, the base case has to be for a particular number. Now, in this case, I cannot use 0 because 0 does not fit into the pi format, but 1 does.
But usually you want to pick like
Usually it is basically the definition, because when you look at a recursive definition of a function, there's one thing that it will stop at, and you can just work with that. All right, any other questions? Can anyone see, just vaguely, how proof by induction has a close relationship with recursive subroutines? Yep. There's a very strong correlation between those two. Because with a recursive subroutine, if you can prove the correctness of a recursive subroutine for the base case, where it does not do any more recursion any further, okay, if you can establish that proof, that becomes your base case. Then you can say, assuming the recursive subroutine works for case k minus 1, now we only have one induction step to prove for case k, then you prove the recursive algorithm is correct for all cases. So it's a very powerful proof technique and is closely related to programming. All right, so that's number 5. This is question number, question number 4. This is the last question, which is question number 5. And I think for those of you who are really itching to do some real programming, you're gonna like this one a lot. Okay, so the following is one way to implement string compare, and in this case it's string compare, not string and compare. You might want to do it for string and compare as well as an exercise, but I'm just dealing with string compare here. Okay, how many people still remember what is string compare? Okay, a few people seems to know something about string compare, and I'm assuming the rest, you only learn about the comparison operator on strings because, this is not object-oriented programming. We stay away from C, function calls. But anyway, this is string compare. It is just comparing two arrays of characters until we find a difference. Okay.
Or a literal string.
Hmm?
It will compare literal strings too.
Well, yeah, it will compare any string, any array of characters. A literal string is really just an array of characters with no name. All right. So the question is, re-implement string compare recursively. That's it. Just give me the recursive version of string compare. Now, how would you do that?
You'd have the function call on itself.
Yep. I want string compare to call itself, but it has to stop eventually. So you will have to figure out, okay, in this case you can stop and I have the answer right away. Okay. In this case you can stop, I have the answer right away. Hold on, in this case I cannot stop. I will have to call another invocation of string compare to get the answer. Yep.
Well, considering what you have there, would it be really easy?
Well, let's take a look. Okay, so
because it returns either 1 or 0, like actual string compare returns 1 or 0. 1,
no, it returns
the late.
Let's find out what is the actual string compare. Okay, the way I wrote it is does conform to string compare, the actual function. Okay, so this is the actual man page of string compare, The string compare and string n compare function return an integer less than, equal to, or greater than 0 if s1 or the first n bytes thereof, in the case of the n version, is found, respectively, to be less than, to match, or to be greater than s2. Now, this return value documentation is definitely following the fine tradition of making documentation as
ambiguous as possible.
Yes. But using correct English grammar all the way. Yes. Okay, so what it means, if the first string is less than the second string, it returns a negative value. If the first string equals the second string, it returns exactly 0. If the first string is greater than the second string, it returns a positive value. And I can see a few smiley faces here because they're taking assembly language programming. And this is what we're doing in assembly language programming, except we're implementing this in assembly language, but not recursively. Not yet. All right. So how would you do this recursively? So this is one way to implement it. Yep.
I'm guessing you replace the while with if, but you keep the same thing, and then instead of the plus plus s1 and plus plus s2, you do a return and then string compare s1 plus 1 and s2 plus 1.
Okay. So that's good. Okay. But how did you come up with the base case? How did you figure out the base case from the description of the while loop? Now think about the meaning of the condition of a while loop. What does it mean? Let me go highlight, the whole condition here, and then you guys can tell me.
It's the termination.
Okay. Well, okay. This condition is not the termination. This is the negation of the termination condition. Okay. Very good. Nonetheless, the termination condition is related to recursion in a very important way. How is it related?
Does it give you the base case?
It is the base case. The negation of this is the base case. Okay, this is when we don't have to go for another iteration. We can stop because we got the right answer. Okay, very good. Okay, so this is the first step. So the first step is to look at the stay in loop condition and negate it so it becomes the base case condition. So that means when you write string compare recursively. So I'm just going to write the whole thing here.
Yeah, but doesn't the string compare only compare 8 bytes of a string? The string yeah. Doesn't only compare the first 8 bytes.
The first 8 bytes?
Yeah.
Okay. Well, let me just do this part first. So I'm looking for the negation of this. It becomes the base case. All right. There we go. Now can someone tell me what to do here? Because I know where the cursor is the base case. We are not going to do any recursion in this case. So that means when this condition is true, okay, the negation of whatever s1 points to is not null, whatever s2 points to is not null, and whatever s1 points to is the same as whatever s2 points to. If this whole thing is negated, we know this is true, this is a base case. What can we conclude? We should be able to return stuff at this point.
You can return s1 minus s2.
Well, this is a negation on the outside, and we have conjunctions in the inside, right? And what do we do? This is a little bit harder for me to read. Can I change the format of this condition in a way so it is easier to read? We can use De Morgan's law.
Not s1 or not s2.
Yep, exactly. We can apply De Morgan's law.
Or not s1 is equivalent to s2 as well.
Yep, so if we apply De Morgan's law, this becomes, all the n's becomes ors, and everything is negated. Okay, so let's see what it means here. It means that the first string, I have reached a null character in the first string. I might have reached a null in the second string, or they are not the same. Is that okay? Does everybody see how I just applied De Morgan's law, changing a conjunction of stuff into a disjunction of the negated version of the original stuff? That okay? All right. Okay. All right. So we'll take a look at each case and find out, okay, but what does it mean? Okay, we'll take a look at this case first. What does it mean when they are different? In other words, in comparing byte by byte or character by character in an array, we are now encountering, hey, the first array has something that is different from the second array. If you're just comparing, isn't that conclusive and say they're different and I know exactly how they're different? Right? Okay, so let's go for that case first. Okay, so we'll say in here, we'll say if S1, whatever S1 points to is different from whatever S2 points to, just return this. Return whatever S1 points to minus whatever S2 points to. That would be my answer. Because if whatever S1 points to is less than whatever S2 points to, the first string is less than the second string, I'm returning a negative number. If they are the same, well, if they're the same, we'll catch it with the other cases. But is that okay so far? Yep.
Was that the return of the while?
Say again?
Was that the return of the while, I think?
Yes, it is.
Okay.
Yep.
So is that right?
You need just forget that it's also true. One of them is
Right. Yeah, but we'll do the simplification later. We'll just say, okay, for this case, we got it handled. Okay. So now, what about the else portion here? Now the else portion is kind of interesting because this is the else inside the if. So by the time I get to this particular else, I know that whatever S1 points to is the same as whatever S2 points to. They are the same. But from the condition, the overall condition, we know that at least one of these is pointing to a null character. Hold on a second here. They are the same, and at least one is a null character. What is the conclusion? They are both null characters, right? If they're both null characters, that means I have compared everything that I can possibly compare, and I'm hitting the null terminator at the end of the string. What conclusion should I give in this case? A 0, or I can still maintain to return S1 minus S2. Okay, dereference S1 minus dereference S2, because that will still be the same. 0 minus 0 is 0. Wait, if the then case and the else case are returning the same thing, why make a difference? Yep, we'll just simplify it to just that. Well, good thing this is all getting recorded so you can actually see how I change the program over time. All right, this is the base case. So what about the non-base case? What about the case where we have to go for the recursion? Okay, if we go for the recursion, it means this entire thing has to be false. Okay, if this whole thing is false, what are we going to do? We are basically saying, if this whole thing is false, it only means one thing. S1 and S2 are pointing to the same character, and they're both not null characters. So we are basically pointing at one. S1 is pointing to one character. S2 is pointing to another character. They are the same. So we cannot make any conclusion yet at this point. Now in the iterative version, we just add 1 to both pointers and do it again. But in this case, we can say, hey, you know what? I'm too lazy. I don't want to deal with this anymore. I'm going to ask the next guy to deal with a substring and tell me the result of comparing the substring. But what substring are we talking about? The string that starts with the next character. Are we doing okay so far? I can rewrite this in another way if people are not comfortable with pointer arithmetic. Is everybody okay with this, or do you guys want me to use the non-pointer arithmetic way of doing this? Huh? This is fine? Okay. Is that making any sense? That's the answer. That is the solution. Turning string compare into a recursive form.
Can you show the normal other way? Can you show the other way?
Oh, the other way? Sure, I can turn 1 into the other way. That means exactly the same thing.
Oh yeah.
Yep. The address of the second element of an array is the same thing as a pointer plus 1. Yep. Don't you like seeing, there are so many confusing ways to do exactly the same thing?